Our next building block is hands down the most important one for this unit. It is voltage. Voltage. Or electrical potential. Both terms work. Electrical potential, which is why we're actually going to give this the symbol capital E, even though the unit itself is capital V for volt, which is actually equal to a joule per coulomb. Joule, you hopefully remember, is a unit of energy, and coulomb is charge, as we've been discussing so far. In electrochemistry, we define this potential as how much energy we can get out of electron transfer. How much energy we can get out of electron transfer. Out of electron transfer. And by electron transfer, we're really discussing redox reactions, since that's what happens in these kinds of reactions. Electrons go from one species to another. Now, a voltage or electrical potential can be positive or negative in value. And if we have a positive potential, that means that energy is released by reaction. Energy is released by reaction. This is the opposite of what we learn in thermodynamics when we learn about delta H values, where we say a negative delta H means energy is released. Voltages are opposite in sign than, say, delta H or delta G. But we don't need to review all of those thermo ideas in this course. We just need to know positive potential means energy is released, which is favorable for the universe, and negative potential, as you might guess, means that energy needs to be put in for the reaction. Energy needs to be put in for the reaction. It is an unfavorable process. It will not spontaneously happen. You have to make it happen. Now I'm going to do a sample problem, and after it's over, I'll discuss why it's actually somewhat interesting. But first, the problem itself. If we have 9.00 volts, notice it's positive. That means energy will be released by any reactions. How much work can be done? How much work can be done? And let's put work can be done in quotes, and then underneath define that as meaning energy released. Energy released. So how much energy can be released by 0.0116 moles of electrons being transferred? 0.116 moles of electrons being transferred. And so as always, I start with what I know. I know that I have 0.0116 moles of electrons to work with. I am ultimately interested in how many joules of energy can I get out of that. I don't have a direct conversion from moles to joules, but I do have coulombs to joules, and I have moles to coulombs. So let's do it. Faraday's constant shows up yet again. 1 mole of electrons consists of 96,485 coulombs of charge. That again is just F. And then, according to the problem, every coulomb of charge can release 9.00 joules of energy. That's what that 9.00 volts means, i.e. the electrical potential. And from here, it's just dimensional analysis, what we've been seeing so far. Solve it, we get 1.01 times 10 to the fourth, and we have nothing but units of joules. So when you first saw that 9.00 volts, you might have thought of one of these 9-volt batteries. And that was on purpose. So is that number 0.0116 moles of electrons. That's how many moles of electrons can be transferred by the electroactive chemicals in this battery before it's done. And so knowing how many moles of electrons are in this battery ready to go, we can convert that to figure out how much charge we can get out of this battery before it's dead. And using that voltage, we can then learn how many joules of energy can we get from that charge. And it turns out that amount of energy is enough to power the average American household for about 1/3 of a second. Which doesn't sound like much, but it's not bad for this little doohickey. Did I really just say doohickey? The last building block I want to discuss, which is not mentioned in the book, is power. So let me erase all of this. Power, which has a unit of joule per second. That is the unit of power. And in turn, power is equal to the electrical potential, or voltage, times the current, which we recognize will actually give us units of joules per second, right? Because voltage is just joule per coulomb, and current is just coulomb per second. And we can see those coulombs will cancel, and we'll be left with joules per second. Now, we can also express a joule per second as a watt, which is a unit you've probably heard of in real life before. And so we can say a watt is also equal to volt, the unit of electrical potential, times amp, the unit of current. Either set of units is fine. So if we say that something requires 5 watts of power, in other words, it needs 5 joules of energy every second, that can be interpreted a number of ways. That could mean that it needs 5 volts at a current of 1 amp, since 5 times 1, of course, equals 5. It could mean that it only needs 1 volt, but generate a current of 5 amps. It could be something in the middle, like 2.5 volts times 2 amps. And the way to interpret something like this is that imagine our device that's taking this 5 watts of power has a battery that's 2.5 volts, and the reactions are able to go fast enough to generate a current of 2 coulombs per second. One of the problems in the first electrochemistry-based homework is designed to really link all of these ideas together in a practical situation that most, if not all of you, can appreciate. But that's it for our building blocks. Next we'll get into actual applications of electrochemistry.